Hi, this is part one of our exploration into emergent phenomena. This is simply an intro video, so there wasn't much content on this particular lesson, but we'll be going over some of the material that they went over. So the first concept in emergent phenomena is the length scale. So that the length scale is defined as, or at least how I define it, because they gave a definition. But how I see it is that it is a mutually exclusive domains. So you have one domain in which there are certain properties of the objects while they're interacting, but as you zoom out of that domain and look at it from not as close, those interacting objects can act as a single object, and so those are two different length scales. Does anybody else have any comments on can add to that?
I guess what you're talking about is something that is discrete, and then when you back up, you're taking the whole.
Exactly.
Okay.
Well, so the example they gave was a car. So you can break up a car, and there's all the individual pieces, but then you can kind of zoom out, and then you get the whole car when it's assembled, right?
Yeah, atoms.
Yeah, exactly. Atoms. Another one that they used was foam as well. So there's the individual bubbles in the foam, but then when you zoom out, it's a completely different phenomena, or they're the emergent phenomena that comes out of it.
So the difference between a water molecule and a bunch of them together making wet.
Exactly. Well, so foam, and I'll just quote the lesson directly, where he said that basically, this is what foam is, where it's air bubbles that have a wall of liquid. And so neither air nor liquid have the phenomena or the properties of foam, but when you put together a whole bunch of these bubbles together, it creates this emergent phenomena where this liquid and air mixture acts very differently than liquid or air.
I think the easiest one to think about is sand, right? Because you think about sand is made up out of things which are obviously a solid. Like a piece of sand is just a piece of essentially a small piece of rock. So it behaves essentially like we think a solid does. If you put a piece of sand in a container, well, it just sits in a container, it doesn't do anything. But all of a sudden, when you put a bunch of pieces of sand together and you put them into a container, they sort of act a bit like a liquid, but not really. They kind of take the shape of the container, but they maintain their shape as well. Like they don't go flat across like, well, a liquid doesn't either because it has a manicus. But basically they'll make little dome shapes. But when the important thing is, you can't really get any understanding at all about how a sand dune works by looking at a piece of sand. The sand dune comes from the interaction of sand with other pieces of sand, and the only way to see that interaction is to step back from looking at a piece of sand on a big enough scale to see the interaction, and then you start to see, okay, this group of things could have properties that the grains don't have.
And the interesting thing with sand, too, is that the emergent phenomenon goes not only up the chain, but also down the chain. So there's different types of sand, right? So a sand dune, when you actually zoom in on the particles, they're actually quite smooth because they've been rounded out from all of the wind and them rubbing against each other, while things like beach sand or sand that is underwater has a much more crystalline structure to it. It's not very rounded out. So the higher level phenomena will actually affect the lower level composition, and that lower level change in composition will then further go back up the chain, which is kind of interesting. Okay, so another one that he talked about was ketchup, which is interesting. So where you have a very complex soup of organic material. And the fascinating thing about ketchup, actually, he didn't mention this, but I'm sure he will probably at some point, is that it's actually a non-Newtonian liquid. But it's a non-Newtonian liquid in a much different sense than the cornstarch and water one, because the cornstarch and water one is non-Newtonian in the sense that when there's force applied, it actually becomes thicker. It actually resists the force. Well, with ketchup, the interesting thing is that it's a non-Newtonian liquid in the opposite direction, so that when there's force applied to it, it will actually become thinner. If you may have noticed that when you're squeezing a bottle of ketchup, you actually initially have to squeeze harder, but then as soon as it starts flowing, you don't have to squeeze all that hard at all. It's because it's a non-Newtonian liquid. It's become thinner because of the shearing action. And I'm not sure what exactly what causes that, right? But that is an empirical emergent phenomena of the ingredients of ketchup.
Yeah, the viscosity is a function of the pressure.
Yeah, yeah. All right. And so there's some other mention of things like chaotic behavior, and he really only touched upon this lightly, but I think the most classic example of chaotic behavior is the double pendulum, where it's extremely sensitive to its initial conditions, and that even though it's a very simple composition of basically two sticks with two hinges, the emergent phenomena is that it is highly unpredictable. Any comments on that?
Have I seen one, a double pendulum? Is there one in, common double pendulum device?
Yeah, there's one in Google. It's essentially, if you take a straight up pendulum that you would see from a clock,
yes,
and you put a hinge in the middle of it, you will get chaotic or not chaotic, but unpredictable behaviors out of that swinging pendulum, whereas with a pendulum that just has one axis, you can pretty much predict it's going to go here, then here, then here. But as soon as you add a third point or a second point, the behavior becomes erratic.
Right, and you could almost say that the more hinges you add, the more it approximates a rope. So that's the interesting part about a double pendulum, is that it acts fundamentally different than a rope, because it's obviously two stiff bodies that are connected to each other by a hinge. But there is kind of that rope-like behavior, because you can kind of swing it around, and the loose end will act on its own, or act independently, obviously, because it has that hinge.
Out of curiosity, is any practical benefit for the double pendulum that we see in everyday life?
Well, no, it's just an example of chaotic behavior, or it's like the classical example of chaotic behavior, and that is going to be coming up in the next couple of lessons. So when we get to that, we'll talk a bit more deeper about that. Okay, so then the next thing they talked about was patterns. So patterns being emergent phenomena, and actually patterns are really interesting in the sense that when we're talking about most patterns, they are actually a composition of other patterns. So you usually can see spots, or you can see stripes, but there's also other patterns where it's both spots and stripes, and not only spots and stripes, but then transitions from spots to stripes. So where you have stripes on one part of the object, and then it kind of fades into spots, and then possibly fades back into stripes, and that's a kind of an additive composition of these patterns to create more complex patterns. And it doesn't occur just on animals either. I mean, there's other very interesting examples, like plants, things like cracks in dirt, obviously snowflakes, different kinds of coral growths. All of these have patterns, and they're all emergent phenomena. You have these small building blocks, and they assemble together and create very complex structures that, even though they're made of simple things, they exhibit very interesting structure globally, when you go up a length scale.
Have you heard of that optical illusion where it's what color is the dress, and it's made up of several discrete dots? I think it was last year. People couldn't discern what color the dress was, whether it was blue or whatever.
Oh, Joe, thank you, by the way.
Yeah, yeah, that's the double axis pendulum.
Here, let me broadcast you for.
Hey, I think there was an algorithm at one of the AI guys. What was it I saw? I saw something on TV about that. I think it was. Just give me a sec.
And so one of the interesting things about a double pendulum is that, so now imagine that you just very slightly adjusted the initial conditions. That line that you're seeing being drawn would be completely and utterly different after a couple of seconds of this pendulum's moving. And that's classical chaotic behavior where it is very sensitive to its initial inputs. And obviously the emergent phenomena is the path that it takes.
It still
it
does
possible-
obviously. Sorry, it still does obviously make that dome shape thing though.
Yes, yeah, like an upside down dome.
Yeah.
Is it
Yeah.
impossible to predict that behavior? Or is it-
Exactly. Well, yes, like I said, very slight changes in the beginning state will cause massive changes very later on. And actually, that was one of the definitions of an emergent phenomena, where it is a phenomena that is highly that becomes more prominent later in a system's life cycle. So the phenomena, its path, it becomes more prominent as it evolves, and so very slight changes in the beginning can make very, very different paths, and that difference becomes more and more prominent as the system evolves.
In terms of human societies, one thing that I kind of thought about was I don't know if any of you are familiar, but there's a philosopher called Baudrillard, and he had a theory about simulacra, which was basically that depending on the beginning state of a simulation, this kind of like emergent behavior can exist throughout time in human societies. So that's kind of what I thought of, was how this type of behavior not only applies to a mathematical formula or particles on a granular level, but it also applies to how actors exist in some kind of axiomatic framework or like behavior system.
Absolutely, actually, and to kind of go in that direction, I posted on my Google Plus profile a very interesting simulation that was done recently, where they modeled different types of societal behaviors. So they had basically the two main ones were the altruistic or humanist position, and then the other one was the tribalist position. And what they did is that they simulated these digital societies where they had certain predispositions for either being altruistic or being kind of more tribally minded. And the fascinating thing, the emergent phenomenon that was found from this, was that actually it seems that the humanist strategy is actually, as you go further through the simulation and you make more and more simulations, it seems that it is always beaten out by the tribalistic model. So civilizations that care more about their people than the outsiders, they have a very high in-group bias, tend to survive much longer and thrive than groups of people that have very high out-group preference.
Agreed, but that's environmentally dependent.
Excuse me?
That's environmentally dependent. You could create an environment that would be more conducive towards the altruistic tribe, the altruistic digital population, and they would win.
Well, locally,
actually, no,
chaos theory would dictate that the best strategy is what they call tit for tat with
that is true.
mercy. I think it is what it's called. In other words, you push back equal for equal. So that means if somebody pushes you, you do push back, but every now and again you do the merciful thing. And then whenever you're adding more than 2 points in the pendulum line, so to speak, in other words, when there's more than two entities in the process, that's when it what he had said becomes relevant. That means that the best strategy is those that have more of a cooperative bias. They become stronger and more coherent over time because there is strength and unity in the community, and that's just the way the math works.
Absolutely. Actually, and to kind of go in that direction, I posted on my Google Plus profile a very interesting simulation that was done recently, where they modeled different types of societal behaviors. So they had basically the two main ones were the altruistic or humanist position, and then the other one was the tribalist position. And what they did is that they simulated these
Well, and I don't know if this is modeled in chaos theory, but the way that I would see it is that it would start off at one point and then steadily increase to an increasing amount of variables, but then it would then fall into one point at the end of the simulation, or it would start as many points and then conclude into one point, right? So that would be the emergent phenomena. I think categorization would be trying to differentiate between the side effects of each of those variables and see how many combinations of variance can occur between each side effect.
Sorry about that. I tried to screen share, but for some reason it's not working. Actually, do you mind if someone screen share that?
Because you're presenting me.
Yeah. Oh, okay. Okay.
I'm going to unpresent.
Okay. Let me see. Hopefully this doesn't crash me again. All right. Do you guys see that?
Okay.
All right, excellent. So this is from the paper that I was talking about. So as you can see, humanitarianism can actually win out at the beginning, but actually the longer the simulation goes, ethnocentrism will usually win out. And as you can see, selfishness and traitorousness never win. And it's a very fascinating paper, actually, where it's on my Google Plus page, so if you guys want to watch it. And actually, I'll link some of this stuff actually. So if you guys could actually give me the links for whatever you guys are sharing, I will definitely put it into the comment section so people have access to it.
The other thing that I think is important to recognize in terms of the proof being in the pudding for cooperation and its effect on success in terms of survivability and sustainability, etc. And that just means that a creature could be more relevant through time, is that eusocial creatures are arguably human and also, but definitely ants and termites and things like that, and they are the two most successful creatures on the planet in terms of biomass. So the cooperation of the young, the distributed tasks, and all of that sort of characterize our social scheme.
Oh, exactly.
And our cooperation scheme seems to have a net effect of being able to go anywhere, do anything almost. Ants and people are all over the planet, and no other creature is like that.
Well,
they're all environment specific.
I agree. And the fascinating thing actually about the ant models, Google had a programming competition where it was simulating ants. It was basically you would write a program that you would have an army of ants, and they would gather food, and then you'd have other competing ants, who there's competition, and you had to fight the other ants, and the person that won, actually how they modeled it is that they did not have a massive global strategy. A lot of people tried to do that, where they would just have like their program that connected to the competition servers. Some people would actually model it by having kind of this god thing that controls all the ants. But actually, the person that won went completely the opposite direction. He made very localized decisions. So the decision making for each individual ant did not depend on any of the other ants. The decision making was solely done for that specific ant, and didn't take any context at all into the, or maybe some context, what was within its range of vision. And so that's an interesting thing where you talk about this highly distributed network of interacting agents, where it seems that even in our programs that modeling how ants actually work as these individual agents rather than having some kind of god program that controls all the ants is much more, yeah, exactly, an overmind is actually much more of an effective method of controlling these kind of little agents. So I found that very fascinating.
Why haven't they risen the dominance of this planet on the surface?
Well, technically, like Joe said, I mean, they have the highest biomass.
Yeah, they have raised the dominance if you count. It depends on how you measure it. Yeah, it's biomass. Then ants and termites and the Hymenoptera like creatures, the ones that are highly social, are the most successful.
Hmm.
In fact, if you take a look at what's been, how eukaryotic cells are like thought to be a bunch of different organisms, prokaryotes that are working together to form a singular membrane, they were more successful. And then, metazoic creatures like ourselves, we have these multiple organs and we're multicellular, and we also have relationships, symbiotic relationships with lots of other things. The more highly social you are, the more that it is able to operate dynamically and continue coherently over time. It just seems to be more prevalent that the higher social you are, the more successful you are over time, because the more dynamically you're able to respond to the variables of the environment.
Okay, what I believe dominance means on this planet, on the surface of this planet, is that they can maintain control of an area of it. We know that we can knock ants off any part of the surface of the planet that we want, so we are the ones that dominate this planet purely through our intellect.
Yeah, like I said, it depends on how you measure it.
As far as them, existing along with mankind, sure, I guess you could, but I wouldn't call that dominance.
I'm not necessarily sure, though, that dominance over a certain area of land is even well defined. So if someone could elaborate on that.
Okay, we wish to control that area and have it bereft of ants. We can do that at will.
Well, I mean in the sense that establishing presence in a certain territory, would that be dominance if we still host other species in that area anyway to augment the territory?
No, it's just simple on space. What I said, it's like if we wish to have no ants in an area, we can do that. So we dominate.
Oh yeah, absolutely. And there's even these new things where they've taken like funguses out of the Amazon that attack ants, and so what you can do is actually it will so there's the two stages of the fungus. There's the spore stage, and then there's the actual growth stage. And interestingly enough, during the spore stage, the ants are completely scared. They hate the spores. But when the spores actually mature and it actually starts growing into a fruit body, the ants are highly attracted to the fruit body. And they eat the fruit body, and then what happens is that the fungus basically completely takes over the ant, and then it starts growing inside of the ant.
Can you post the live link? Sorry, dude. Can you post the link to that video? Is that a sausage they're hauling off?
No, that's a millipede.
It's a worm, and yeah.
But like I was saying, the fascinating thing is that so they when it's fruiting, they love the stuff, and then it infects it, and then what happens is that after they eat it and it grows inside of them and then releases a whole bunch of spores. Now you have a whole bunch of spores around like your house, right? And so because they hate the spores so much, they act as a very excellent deterrent. It's almost a non-chemical way. It's a kind of using nature to take care of the problem, and it's been shown to be effective for multiple years because the spores just stay around and the ants just hate the spores.
Like for example, it comes to mind if there's like some higher intelligence that comes into our solar system and decides to dominate this planet, we'd have to adopt the practices of ants and sort of co-opt, live along with them cooperatively.
Yeah, I think you have to look at it as a dynamic system. In other words, there are some times when people who are smaller have the advantage, and some people, big, large, brutish type people might have an advantage in another situation. But for instance, if we got hit by an asteroid, I think the one that would be most successful would be the bacteria, because they're like buried miles deep and all of that. And so when you look at success, you have to consider a lot of factors and variables that are environmentally contingent. So we are successful in the context of the environment that we're in now, but that could change.
True. We have to be more adaptable.
Yeah, we're squishy meat bags that have very limited comfort zones.
I think there was some science fiction story where they imprinted our, DNA into rocks and stuff because, just that thing happened. There was some cataclysmic event that we couldn't survive, but we wanted, the DNA evidence for us to keep on going in this planet.
Well, even if, like, in the worst possible situation where, our population gets reduced to, like, 10,000, obviously we'd have much less luxuries, but at the same time, we've been just conditioned to accept more of those materials. So I don't think humans would necessarily completely die out unless there was someone that literally went around each house or, and just killed everyone. But that would be interesting. I think if a giant asteroid hit, it would literally have to burn every last inch of soil to get rid of humans, whereas getting rid of endangered species would be much easier, obviously.
Well, something that would reduce the oxygen content of our atmosphere would, get rid of a lot of living creatures.
Right, but if you were to build a dome or something in enough time, there's a supply of oxygen somewhere, so someone probably has access to, something that they can breathe, and then it would become like a, what's that video game called? I'll think of the name. It's Bioshock, where everyone's underwater and they have to sell the oxygen, and it's like a critique on capitalism or whatever. Because
objectivism, yeah.
Yeah.
Well, you think about it. Does mankind necessarily have to exist in a biological form? Can we exist in, digitally?
Possibly, but
That's an interesting question.
Yeah, I think that who knows? It could be an emergent property of this universe, where the most highly evolved organic life chooses to transcend simply because it's more convenient. But then you have to ask, well, if we do that kind of stuff, does that mean we create a similar universe where none of these tragic events can occur, or is that already the default state and we don't have to worry about it? And that's the argument the creationists use, that we don't necessarily need to do that because that's already the emergent property of the universe.
There's an argument, not an argument, but I mean the jury's still out, I think, on whether emergence as a concept is descriptive or prescriptive. In other words, is it just reporting an event? It doesn't have any predictive power, so what is its use except in terms of recognizing a pattern? In the same way that you say, if that person cheated on me 20 times in the past, I can infer that it's probably going to do the same again in the future, but it's not predictive in the sense of like Newton's laws where you could say this and then precisely this thing happens. We can't predict what's going to emerge out of a system.
You're touching on one of the things that has kind of been nagging me a little bit about the introduction to this course, too, right? They're almost presenting like either you're a reductionist or you're an emergentist, and there's no necessarily, you can't really be a compatibilist. And I don't know about that. Just because complex systems emerge, or in any of these ways that they're using as examples, I don't think it means that, that must mean that there's actually something happening there. And it's not clear, really, at least so far in this introduction, that they're claiming that if we really could know all of the variables and how they operate on the tiny scale, then we could predict the emergent properties and how the system would act on a larger scale.
Well,
they seem to be claiming that we couldn't, but then again, maybe that's just because of our limitations.
Well, the
Right, I
research
think it's more of a practical limitation than an actual physical or philosophical limitation.
Well, what do you mean by that?
Like you said, it's a practical.
Is it a feature in the system itself, or is it something about, kind of what's wrong with us. We're not smart enough.
That's what I'm saying. Yeah, I think it's a practical problem where we just don't have the insight necessary to completely reduce it, I guess. But I would agree. And to be honest, I think, to be fair, they obviously this course is going to be very biased. They're going to want to present the emergent side, and they'll compare and contrast. But I don't think they're necessarily saying that reductionism is bad or unnecessary or something. I think
I'm not saying that they're saying that it's unnecessary or bad, but they seem to be presenting them as though they're opposed to one another. At least in this intro, they are.
Yeah, yeah, it kind of does seem they make it out to be a dichotomy, but I sort of thought that they were just making a short list of the types of deconstruction you could do on this type of study, but since they're going specifically after describing emergence, it is brief, and it is probably a study of its own. And the question you brought up about the epistemology, the limits of human knowledge, that's also an interesting part of this too. So hopefully that'll be brought up in the consciousness section.
It kind of looks a little bit like they're leaning on the epistemological problems in order to sort of beef up emergence.
Right.
And by the way, I love that Joe put this picture up. So this is the Game of Life, which is probably one of the most fascinating emergent systems out there. I was putting up Lindenmayer systems, which are kind of interesting. They're a bit more easier to understand than the Game of Life, but the Game of Life itself is actually pretty simple. Have you guys heard of this that specific simulation that he's got right there?
Absolutely.
Yeah. Oh no, I know. I'm sure.
I think it's beloved by probably all of us.
Right. Well, just a really quick overview for who hasn't seen it or doesn't know about it. It's a very simple rule set. Basically, if you look at each cell at a time and you look at its neighbors and you look at all 8 neighbors around it, so both the north, south, east, west, and then the diagonals. And what you do is that you say, okay, if there's 0 or 1 neighbors, it dies from loneliness. But if there's 2 or 3 neighbors, then it survives. But then if there's more than 3 neighbors, 4, 5, 6, 7, 8, then it dies from overcrowding. And that very simple rule set leads to this highly emergent phenomenon that you're seeing right now on the screen.
I don't think a case needs to be made for reductionism versus emergence, as if there's some kind of dichotomy. Like, the way that I would think on it is, like, for example, when you do some problems in physics, some are very easy to do if you use sort of a Newtonian method and you look at positions and the equations of motion. Some are very easy to do if you look at them from an energy perspective. It doesn't mean like one of them is right and one of them is wrong. It just means that sometimes a different perspective is needed in order to see something with sort of ease. So it would be possible, if you knew the Hamiltonian of every grain of sand, including the interactions between all the other grains of sand, that you could predict that it would look like a sand dune. But just imagine the kind of complexity and calculation that you're talking about between the intermixing of millions of particles with other particles, and like the staggering number that comes out of that is crazy. So maybe there's another way to look at it as sort of a group in which you're looking at interactions of a group in and amongst itself and finding patterns in it. So how do we do that without having to look at a million interactions between a million things? Is there another way to look at it? I think that's what they're trying to get at.
I hope that's right. I didn't get that. I didn't get that vibe, at least from this intro. But I sure do. That would be, to me, the optimal way to present all this material. So we'll wait and see. I sure hope they do it that way.
I think the work that Stephen Wolfram has done on cellular automata has also some really good implications in terms of recognizing how emergence happens and how unpredictable it can be. In other words, if you start from a certain position and reduce it backwards, you can't necessarily predict. In other words, there is a top-down sort of effect that happens that is unpredictable, as well as a bottom-up thing that happens that is unpredictable based on some pretty trivial mathematical variations in the
like the fact that Rule 34 is Turing complete. to kind of explain that simply means that the specific system that Joe has, I don't think it's that specific rule set, but in that general category of systems, there are certain rule sets that act as a universal computer. So you can actually use this very simple rule set, plug in some inputs, and you just run it, and then it will actually exit with a certain output. This ridiculously simple rule set creates this very complex emergent phenomenon that can express string completeness.
Excellent.
And so the other thing, actually, that I wanted to show was that here, just let me get on the screen really quick. Was the Lindenmayer system. I don't know.
Take your time. Yes, very interesting hangout so far. It's just
Happening with my screen sharing. All right, here we go. Sorry about the delay. For some reason, screen sharing's a little. Here's another very simple rule set. So what you can see here is that here. Let me, you see my mouse?
yes.
Right here. Okay, so here's the first iteration. So as you can see, this is iteration 2, 3, 4, and 5. And so the simple rule is obviously in the first iteration, it's just the stick. But in the second iteration, what you do is you add this on the right, you add this higher stick, and on the left, you add this lower stick. And so for the next iteration, what you do is for every single stick, you apply that rule. So here you go. You see this small piece right here looks exactly like this. And this small piece right here looks exactly like this. And this small piece right here looks exactly like that. And then as you can see, you just keep repeating and repeating this exact same rule. And the more you repeat it, the closer to a fern or a leaf. And you could do even more complex rules, so where you create a little ball right here instead of just a stick, and I'll make it look like a leaf or something. And actually, these Lindenmayer systems are used in video games and a whole bunch of stuff to generate scenery, because what kind of graphics designer would want to spend their entire life making trees, right? Or might as well just have them these unique trees generated from you from
computed
kind of
in
algorithm.
milliseconds.
Right. And so what they do is that, so instead of following the rules precisely, they'll do it probabilistically. So sometimes they'll leave off one of these things, right? So like here, they might leave this one off. And that will change the output of the system after a couple iterations. So if you add a bit of randomness to it, it creates these random unique trees, and you just have to run it again, and you can have millions of unique trees in a couple of seconds.
Excellent.
And there's also Boids. Actually, Joe, you had that picture of the birds up there, but there's also another very simple system called Boids, which it's three simple rules. So you have these simulated birds that are all kind of flying together, and the three rules are basically go the same speed as everybody else, go the same direction as everybody else, and avoid your nearest neighbors. And those three simple rules create that complex phenomena that Joe has on screen right now here, where this kind of flocking behavior is completely described by these three simple rules.
Excellent.
Yeah, that's how genetics works too. In other words, and I'm going to be real crude here, but say that there is no map of all of your arteries, for instance. There is just a simple rule that says go this
Branch
far
here
in relation to this width, and then bifurcate until you can't anymore.
Yeah, it's kind of like a Lindenmayer system almost. All right. And so I guess the last example they had was so a thin amount of oil in a pan. So where if you've ever done this before, where you put a little bit of oil in the pan, and then you start heating it, and then all of a sudden you see these convection circuits that are being made, where you start seeing these patterns form in the oil because there's these convection currents that are happening inside the oil. And these patterns will actually stabilize based on the shape of the pan that it's in and how much oil there is. And they typically stabilize into hexagons. So that's pretty interesting too, I guess. Let me see. Other than that, oh, okay. And so the other thing, so I actually have another example. So my screen is the picture that you can see right now. That's my profile picture. Is actually an oscillatory chemical reaction, which is another kind of emergent phenomena where, as you can see, the chemicals will kind of eat each other in an orderly fashion depending on what state it's in, and it'll quickly transition between different states depending on the local state around it, and it creates a highly complex phenomenon that you see here.
I think another interesting point is if you look at cymatics, certain sound frequencies will bring sand schemes into order. And I think that's pretty fascinating. That it seems like there is so certain places of vibration that bring order, and then other things which bring chaos, which is not a lack of order, really. It's just a different form of order.
Well, right, and it's also constrained by the object that you're vibrating. So it's usually done on like a square plate, but if you do it on a round plate, the frequencies that it interacts with and creates the either chaotic or non-chaotic patterns depends not only on the frequency but also the shape of the plate. So these very small changes in the initial condition create very big differences in the global presentation, so to say.
Yeah, would somebody out there please do it three-dimensionally, like in an aquarium or something, and then film it, please? I've been looking for that forever.
Gosh. Oh, and so probably the last example, and I guess we'll wrap it up because, like I said, this is the intro, so we don't really have a specific topic other than what they started. But my last example, at least, is physical computation. So where physical computation is actually exploiting the laws of physics to do computation. So you're not actually using computers, you have physical devices that do the computing for you. And obviously what might first come to mind is maybe some sort of like ball and marble contraption, but there's even simpler forms of physical computing. So the most simplest is actually if you take two pieces of plexiglass where you kind of have them side by side, and then when you have pegs that are placed in this plexiglass, and what you do is you dip the plexiglass into the water, and what happens is that it's soapy water actually. It will actually create what's known as a minimum spanning tree between the pegs, and that's actually a very difficult problem to solve with computers. It's actually what's known as an NP complete problem, which means that it's pretty difficult. Or no, it's not. No, it's not. I don't think it's NP complete. I think it's like n squared or something like that. It's a pretty ridiculous algorithm. But what you can do is you take this plexiglass with these pegs and you submerge it in water, and then as soon as you pull it out, basically, just from the physics of the bubbles interacting with the pegs, bubbles will obviously always try to find their lowest energy state, and so that property of bubbles, that's what a minimum spanning tree is. It's the lowest. It's the shortest distance, or it's the connection between all the pegs that creates the shortest. If you count up all the distances between the pegs, it's the shortest one. And the interesting thing about that, though, is that physical computing has its limits, though. So when you submerge it and then you pull it up, if you have a whole bunch of pegs sandwiched in between your plexiglass, what will happen is that it will not always find the optimum solution. It will actually usually fall into what's known as a local minimum. And actually, this is a very difficult thing with computers in general, but it also manifests itself in these physical computing systems where when you dip it out, it's pretty close to the perfect ideal solution, but sometimes you have to kind of like blow into it to kind of add a little bit of extra energy to push it out of its local minimum and to push it into the global solution. So it's interesting that even though we can kind of exploit the laws of physics to do some of this computation for us, there are still this fundamental physical limits. Just like with regular computers, the fundamental physical limit is the speed of light. But with some of these physical computers, obviously they're toys compared to real computers, the fundamental physical limitation is just how many pegs there are in this board.
Okay.
Mm-hmm.
Physical computing.
Yeah, that's it's a very fascinating topic.
Other than physical computing, what do they call that?
Just Google it, just physical computing. There's a whole bunch of examples. The most common one, like I said, is that pegboard with the bubbles. But there's other ones like doing statistical stuff with like marbles and that kind of stuff. But the most interesting one, the simplest one, is the peg example with the bubbles.
See, to the materialists, all computational devices have to be physical, don't they?
Well, yeah, yes, no, but physical computation means a very specific thing, meaning to use the laws of physics, what we have around us, to, right. And in a sense, that's what computers do, right? They're exploiting quantum mechanics and semiconductors to do that kind of stuff. But there's other forms of computing that we can do that are radically different than that, like computing with bubbles, right?
Okay. I have to study up on that.
Yeah, it's fascinating. It's pretty simple. I think I try to explain it as well as I can, but there's videos on YouTube where they have demonstrations where you can literally see what happens, and they talk about like how it doesn't perfectly solve it sometimes. You have to kind of blow in it to make it give the correct solution and that kind of stuff. All right. So anybody else got anything else, or I think I'm pretty happy with today's hangout. It's obviously just the introduction one, so there isn't too much to talk about.
Maybe you should plug when the next one is going to be.
Oh yeah, so the next one's I'm thinking of just doing it every Saturday. So for the next 7 weeks, it's an 8-week course. So this is the first part. We'll have it about midday, just so that we can get as many people on as possible. And yeah, don't worry if you haven't gotten into the course yet. It's Coursera is free, so you just sign up for an account, and we'd love to have you here talking to us.
Are you in the UK? Because this is like 5:07 Eastern.
No, I'm California.
Okay.
Yeah, okay, so it's 2 o'clock right now. I know, midday for me, but yeah, I try to keep it nice, so like the East Coast, because it's kind of it's a bit later on the East Coast.
Yeah, I was just sort of pushing for clarification so people would know about what time it is in their frame of reference.
Yeah, because right. Saturdays are really hangout full day, and yes. I haven't been able to put mine up because of how full the day is. So do you mean sort of around the same time?
Yeah, and we'll try to keep it. I'm not going to try to limit it or try to force it into any specific kind of pattern or anything. It'll be really open. Anybody who's following along with the lessons are welcome to join, and kind of just a free-flowing conversation about what we find interesting. So.
Are there materials other than the discussion here?
Yeah,
no, that's it. We just want the people who come into the hangout to watch that week's lecture. They're usually pretty short. I think all of them are under an hour long. Obviously, this week's lecture was only 11 minutes, so it was a very short one.
Can you please link to the lectures?
Yes. Actually, I will link the lecture. I'll give you that, and I'll link the lectures in the comment box after this is all done.
Great, thanks.
Ludwig, I think you'd love these little lectures.
Oh, yeah. All right, well, thank you, everyone, for coming. This was an excellent start to our series, and we'll see you next time.